Hi, I'm John McMillan, and welcome to today's webinar on MCAD collaboration and co-design. Today, designing printed circuit boards in 3D is not the exception, it's the norm. In the same respect, printed circuit board design isn't done in a vacuum, it's an aspect of product design. That is, we're now designing the mechanical enclosures alongside the printed circuit boards and incorporating the mechanical piece parts for the enclosure, brackets, and the heat sinks collaboratively in the design environment, essentially creating a digital model of the end product within the CAD environment. What you may not know is that poor or lack of electromechanical co-design processes account for projects missing their time to market and cost targets by 50% or more. So if you've not been considering the necessity of electro and mechanical collaboration throughout your product design flow, chances are you're spending time fixing costly mistakes, respinning PCB designs, and missing critical time-to-market schedules. To show you how modern ECAD-MCAD collaboration works, I'll turn this webinar over to Brent Klingforth, one of our technical marketing engineers, to demonstrate how you can overcome the challenges of electrical and mechanical co-design and get it right the first time. Brent?
Thank you, John, for that introduction, and welcome everyone today to our webinar on ECAD-MCAD collaboration. And John, you are 100% right. We should not be using old antiquated ways of moving data from ECAD to MCAD. We should be using the digital information that's available in the CAD tools to make our jobs easier. Why not take advantage of the work that the mechanical engineer has already done in his tool to design the board outline, maybe even place critical components, mounting hole locations, and bring that data directly into our PCB design tool with a couple clicks of a button. That's exactly what I'm going to show you today, and we'll see how powerful this functionality really is and how much time it can save you. The design we'll be using today is a hand drill with some smart electronics. As you can see, the mechanical engineer has already done the job of creating the board outline for us, putting in a mounting hole, placing a connector that's going to go up to a smart LCD display, and adding some holes that wires are going to solder into. So let's go ahead and get started. In this example, I'm using NX for the MCAD tool, but you can use any MCAD tool that supports the IDX interface. While the mechanical engineer has been doing this job, I've obviously been doing my electrical design. So I'm going to go ahead and start my PCB design here by forwarding in my components and netlist from the schematic. Using an intelligent template, I'll have most of my work done for me later on, but to start out, we're just going to get a basic board shape. We'll go into our 3D environment, and from there, we'll activate the MCAD collaboration tool. From the collaboration window, I can see that John has created a collaboration file. I'm going to select that file, and on the right-hand side, I'll be able to see all of the information that John is sending over to me from the MCAD environment. Things like the board outline, mounting hole location, pinhole locations for the wires that'll be soldered in, the LCD connector are all there created for me. So with a couple clicks of a button and about 10 seconds of my time, I've brought in the board outline and placed those critical components instead of wasting 2 to 3 hours of valuable engineering time. What a time savings. The next part of my job is placing components. So let's go ahead and start placing some parts in the usual 2D environment that we're used to. Let's use the convenient Component Explorer window that's available in Paths Professional. As you can see, there's groups of components already created for me from the schematic. I'm going to drag the motor control group onto the PCB, which will place a room of components. From there, I can pull out the individual FETs and place them in their proper location. To assist with the placement of these FETs, I'm going to use a vertical alignment feature for each column of parts to make sure they're perfectly lined up. Lastly, before we move on to more 3D MCAD collaboration, we're going to go ahead and place this PIC controller. By opening a 3D tab inside of Paths Professional, I can now see my board in full 3D. And we can see some of our components already have models assigned to them because they've been used in previous designs. But I have a new component here that I've just recently added into my library. So we need to add a 3D model to this device. To do this, we'll select the device, go up to our 3D toolbar and select Import Model. From here, we'll go search for the step model that I've downloaded from the vendor's website. Aside from the vendor, you can get 3D models from numerous free content providers. Once selected, the part will be imported and placed over the decal. You'll see these large green arrows over the top of the part. These are to help you rotate the part in the X and Y axis. And then we'll use the mating features for the Z axis. As you can see, the part is hovering above the board a little bit. So to mate the part with the actual copper pads, I'm going to use a Define Seating Plane feature on the Align 3D Model dialog box. Once you select that button, You just rotate the part so you can see the bottom of the pin, select one of the pads on the bottom of the pin, and the part will automatically drop onto the decal as the tool already knows the seating plane of the decal. Check our placement by rotating the board around real quick. We can see that in the Z plane, it's perfectly mated with the copper pads, and in the X and Y, it's mated perfectly in the center of the pins, all with a couple clicks of a button. Now, I don't want to have to repeat this process again in another design that I use this part, so I want to save this information off into my library to reuse again. Paths Professional provides a convenient tool to check to see if the parts in your design came from the library, or if we map them locally in the design and need to update the library. To perform this step, click on the Manage Mappings button on the 3D toolbar. Dialog box will open up, and there you can see all the components in the design and if they're library-based or local only. More importantly, I want this part in my library now. So to do this, we're going to click on the Update Library button on the 3D toolbar. And in that dialog box, it'll automatically show us that this part doesn't exist in the library and was manually aligned. In the Overwrite Policy dropdown, I have 3 options to choose from. In this case, I'm just going to choose Overwrite, click OK. That part will then be pushed into my library, so I don't have to worry about this part in the future. We'll go ahead and place a couple more components here, this time on the bottom side of the board, but we'll do it in the 3D space. So again, I go back over to my Component Explorer. I'm going to pick 2 ICs in this case. You'll notice as I pull these parts onto the board, they already have 3D model assignments. This means I must have used these parts in another design. They're also turning yellow when I place them over the top of each other. This is indicating a clearance violation. We'll go into this in more detail a little bit later. Next, we're going to talk about one of the biggest advantages of using the 3D environment for doing PCB placement. To do this, I need a step model of one of the features from the mechanical design. So using NX, I'm going to generate a step model of the heatsink PCB mount. From the 3D environment, we can now import this step model into the design. We can import any kind of step model you want. It can be a full enclosure, another printed circuit board. In this case, it's one piece of the drill that the PCB is going to mount to, but it poses some placement constraints. So we need it in our design to do proper placement the first time. So again, from the 3D toolbar, I'm going to choose the mechanical model import. From this dialog box, I can rotate the step model that I just imported in the Z-axis to rotate it 180 degrees to line it up with that hole. Now we're going to go to the 3D menu and choose Mating Mate. This puts us in mate mode for any 3D type model that we import into the board design. In the workspace, right-click and choose Snap to Access. When you hold your cursor near the hole in the board or the hole in the bracket, you'll see a line pop up. Click on that line, and those parts will automatically mate on that axis. Next, you right-click, snap the face. Click the face on the bracket around the hole. Flip the board over, select the bottom of the board, and the board will move down to the face of the board. Now we have a perfectly aligned mechanical structure with our PCB in a couple clicks. Now for one of the more critical parts of doing PCB placement in the 3D space. Instead of using visual inspection, you want the tool to tell you if you have a violation. So to do this, we set 3-dimensional DRCs. To create the rule, go to the clearance icon on the 3D toolbar. From the dialog box that opens, we can now set our design rules that we're interested in for this design. In this case, I'm interested in a mechanical to component design rule. This rule will prevent us from placing a component that interferes with the overhangs of this heatsink mounting bracket that we've attached to our printed circuit board. Now that we have the heatsink in the design, I can use it to help me place the FETs in the proper location to make sure they mate properly when I place a heatsink material between the metal and the part. To do this, I can go to Displayed Control on the 3D tab. We can add the mechanical part as an item, and from there I can change its color or I can change its transparency. Placing parts in 3D is not always the easiest way to do it. So being able to place components in the 2D space and see the 3D space at the same time is very powerful capability. In this case, that's what we're going to do. I can't really grab the parts with the heatsink over the top of it, but I can go over to the 2D space, move the part around, and see it in the 3D space. Continue with our design, we're going to place a few more components into this project. This is where we're really going to see the power of using 3D. I'm going to go over to the controller group and I'm going to grab one of my ICs and I'm going to drag it onto my design. Now, I want it placed in the lower left corner, but you'll notice as I get close to that lower left corner that the heatsink pops up turning yellow and red. So without the heatsink even being displayed, it's still doing a DRC against our parts that we're placing. The yellow means that we're within the optimal proximity, a little bit of a gap, and the red means we're in collision. If we go ahead and make that heatsink visible again, we can see how difficult it would be to place this part in a full 2D space. You have to have 3D capability to do this effectively without doing iterations. Next, I want to make sure the mechanical engineer hasn't provided too little or too much space for the thermal adhesive that we've chosen to place between our FETs and the heatsink. To do this, I'm going to use the Y cross-section capabilities in the tool so that I can see through the heatsink and over the FETs. From there, I'll go up and use the measuring tool and measure the top surface of the FET to the bottom surface of the heatsink. We've seen real-time DRC in action, but what happens if we had placed some parts prior to bringing in the mechanical structure? To do that, we need some type of batch DRC checking. So in this case here, I placed some parts earlier in the design without the mechanical heatsink in place. Now I'm going to go ahead and run our batch 3D analysis and see if I have any violations in the design. Using the Hazard Explorer in Professional, I can see that we did create a violation when placing those parts earlier, not knowing how much the heatsink overlapped the board. Rolling the board over, we can see the parts, we can move the part out of the way, and fix the violation in a matter of seconds. The mechanical engineer has requested a view of the board to place inside his assembly. So using the collaboration capabilities, again, in Paths Professional, we can export out a proposal. In other words, the mechanical engineer sent us the first version of the board. We're going to send back the second, so not everything's included. Only those things that are different from when I receive the design will be sent back to the mechanical engineer. Makes a much lighter weight file and less prone for errors when importing the data. So we're going to generate that output, go into the collaboration folder, and then the mechanical engineer can go grab that data. Well, the mechanical engineer can now use his collaboration interface, open up our proposed file, see only the differences from what he sent me to what I've sent him. Using preview capability, that he can also preview the change before it actually occurs to make sure he wants to accept what I'm sending him. If not, he can reject certain items, place a note on that, and send it back to me, and I can make the change. In this case, he's accepted all the changes and will import everything into the design. John has decided that in the future he might have to make some changes to the enclosure, which may affect these two parts on the bottom side of the board. So he's going to move them slightly back towards the screw hole in the center to ensure that future changes will not be affected by this part placement. So he can move the parts inside of NX. He can then go back to the collaboration environment, export out a proposed change, place notes on the parts that he's physically changing, output those files into our Exchange folder for me to pick up and bring into the layout. He's notified me that there's a change pending, so I open up the collaboration tool. It instantly finds the file. I select it, and I can see very clearly the two parts that have changed. Down below, I can see the delta and XY positions, but better yet, I can turn on the show physical change, and I can see the part move into the new location before I accept this. After reviewing both of these changes, I feel they are acceptable for the design and assembly and fabrication of this board, so I'll go ahead and accept the change and move forward. Until now, we've been talking about just using the IDX interchange format between MCAD and electrical, but there are cases where you can't use an IDX file, so you would need more conventional outputs like STEP or IGES or SAT or PDF. All those capabilities are available in Paths Professional. Using the export function from the 3D toolbar and the dialog that appears, you can choose these different file types. Based on the file type you choose, you'll have options available for exporting that data. Let's go ahead and export out a step file of this board. To get a view of the board that we exported from Paths Professional, we're going to go over to NX and import the step data. If you're using a mechanical engineering tool that does not support IDX or IDF, STEP is your next best option for bringing a realistic looking board into that environment so that you can do visual inspection. After importing the file, we'll see that it comes in just like we see it in the PCB tool. However, when looking at the navigation tree, we can see that this is not an assembly. It's one solid model. So you wouldn't be able to make any changes to it, but you can definitely use it for documentation purposes. Next, we're going to take a look at a couple other formats. One of those being PDF output. PDF is probably one of the easiest ways to share data with anyone else. Using the same export dialog box, you just choose PDF, it generates the file, and now you can share it. Just like a PDF document for transporting text, it works quite well for 3D. There's a lot of built-in capabilities in the PDF viewer. A couple of those are being able to build a tree automatically, cross-probe any object that's in that tree into the view itself, and also being able to change colors, lighting, and rotating the object around within its 3D space. It's a very powerful and convenient tool for sharing your content. For those companies that do not have an MCAD tool, Paths Professional does allow you to create board outlines and place mounting hole locations from a step file. To import a step file to use as a board outline, you simply go to the 3D toolbar menu, select Import Mechanical Model, go choose your step file that's going to act as your board outline. It will then show up in your design. Now to create the board outline, you go to the 3D menu, you choose Create Board. First thing you want to do is select an edge or face of the step model that you've imported that will highlight in purple. You then want to navigate around to the corner or hole you want to use as the origin point. You'll click there. You'll see a little circle icon pop up at the location. After doing that, you may see a dialog pop up asking you to assign holes that it's found to a pad stack from your library. Even though IDX is a much better way to bring in your data, you're not left in the dark with Paths Professional. You still have that capability of using a step model to automatically produce a board outline for you, whether it's simple or very complex. Like we showed earlier, step file has the capability of taking a full printed circuit board, traces and everything into MCAD. With Paths Professional and NX, you can do that with IDX and have intelligent, usable data in your MCAD environment. One of the examples of using that intelligent data would be thermal analysis, which we'll talk about in a second. For now, we'll just use the MCAD collaboration interface like we have been, but now we're going to use the filter function to help us control what information gets passed from the PCB into the mechanical environment. At the top of the MCAD collaboration dialog box, you'll see a filter-looking icon to the right. When you select this icon, it opens up a dialog box where you can choose all the various options for the data you want to pass over to the mechanical environment. The important ones, if you want metal to go over, is to choose all the electrical layers. Once you hit OK, you hit refresh, and the list down below that, you can see all of the objects that will pass over to MCAD. Using the checkboxes, you can deselect the items that you choose not to pass. Just like we've already been playing with, you open the PCB in an active workspace. You'll open up the PCB Exchange toolbar inside of NX. From there, you're going to choose the Import ECAD icon. You'll select the file that was generated by the Electro engineer. This file will open up. It'll update the PCB. This will update the PCB with all the new electrical content passed over from Paths Professional. From there, we can turn off layers and we can see what the internal layers look like. So we'll do that here and we'll see each of the 4 internal layers of the board and what the copper planes look like. And from the PCB Exchange toolbar, you can also start the simulation process by doing the meshing setup and controls directly from the PCB Exchange. This allows you to go directly into SimCenter and start simulating your design for thermal analysis. Let's recap what we talked about today. As you can see from what we've shown today, collaboration between design disciplines is now mandatory to meet tight schedules we are all faced with today. Being able to visualize and use the design content created by others in the product design team allows you to design faster and make better decisions. Change your design philosophy can be a challenge. However, continuing to do the same old thing only allows your competition to be first to market. Here's highlights to think about for your next design project. Use collaboration available on Paths Professional to reduce design time. Take the upfront time to add 3D models to your library. Use 3D placement to eliminate costly design spins and mistakes. Produce a higher quality product. And lastly, possibly create new ideas, ending up with a better product for your company.